The first set of circuits we're going to look at are resistor circuits. The first of the resistor circuits that we're going to look at are circuits that are resistors that are in series to each other. So resistors that are in series mean that they kind of just fall along the circuit in an orderly fashion. So we can call this V total. We can call this R1 for our first resistor, R2 for our second resistor, and R3 for our third resistor along our circuit. And for the circuit, so the current is going to flow from positive to negative charge along the track here. And for resistors that are in series, there's two important things to remember. The first important thing is that current is constant. So the current does not change as it goes around the circuit. It stays the same. And the second thing is that voltage adds. That means that the total voltage in gets split throughout the circuit, and all of it is being accounted for. So to get a better understanding of this, we're going to look at like an actual example. So let's say we give values to parts of this circuit where we know the total resistance is 6, and the unit for resistance is ohms. So we denote that there. The resistance of resistor 1 is 1 ohms. The current at resistor 3, oops, sorry, that's not ohms, it's 2.5 amps. And the voltage at resistor 2 is 5 volts. We can use our knowledge of Ohm's law so that the current is equal to the voltage over the resistance, and our knowledge of total resistance for a in-series circuit. So for resistors in series, the total resistance is simply the sum of all the resistors. So in this case, it's R1 plus R2 plus R3. We can use these few bits of information as well as knowing current is constant. So current is constant. And that the voltage adds, so the total voltage is going to be, not R, V1 plus V2 plus V3. Using these bits of information, we can fill in this chart. And this is at this point just a system of equations with some unknown variables. If my current is constant, then the current at resistor 3 is the same as the current at resistor 2, 2.5 amps, which is the same as the current at resistor 1, 2.5 amps, and the same for the total current, 2.5 amps. It hasn't dissipated. We can now use Ohm's law to calculate the voltage. We can actually use it to calculate the total voltage, the voltage at resistor 1, and then using that, that the total voltage just sums across the entire circuit. We can use that to calculate the voltage at resistor 3. We could also use the resistor equation to figure out the resistance at resistor 3. There's several different ways we could go about doing this. So the first thing I'm going to do is we're going to calculate the total voltage. So using Ohm's law, just solving for V equals IR. And this is true for each case of the scenario. So for V total, that is then the case of the I total times R total. And in this case, that's equal to 6 ohms times 2.5 amps, which gets us to 15 volts. So that's our total voltage across the entire circuit. We can use this now to figure out the voltage at resistor 1. V1 equals the current at resistor 1 and the resistance at resistor 1, which in this case is 2.5 amps times 1 ohm, which is just 2.5 amps. Or not 2.5 amps, sorry, 2.5 volts. Get your units right. 2.5 volts. I could really go either way with this. I can also use the voltage on resistance to calculate the resistance at resistor 2, but what I'm going to do is I'm actually going to use this total voltage to calculate the resistance at resistor 3. So we know that the voltage of 3, if the voltage adds across, it's going to be the total voltage subtracted from it the voltage of 1 minus the voltage of 2, which in this case is going to be the 15 volts minus 2.5 volts minus 5 volts, and I get that the voltage at 3 is 7.5 volts. Then I can use really any number of situations here to calculate either the third or second resistance. Let's calculate the second resistance. Again, using Ohm's law. So Ohm's law here, I'm running out of space here, but we'll get it all on one page. If I solve this equation now for R instead, R is equal to the voltage over the current, so that the resistance of 2 is equal to the voltage of 2 over the current of 2. In that case, that means I have the 5 volts over the 2.5 amps, which gives me 2 ohms. And then using the total resistance, I can calculate the resistance at 3. Resistance at 3 is equal to the total minus the resistance at 1 minus the resistance at 2. And bear with me with the space. R3 is then equal to my total resistance, which is 6 ohms minus 1 ohm minus 2 ohms, and I get that it is 3 ohms. So the next circuit for resistors we're going to look at is when I have the resistors and they are in parallel. So resistors are in parallel when we see that they split off in junctions like this. So we can have this be the total voltage. We'll call this the resistor 1, resistor 2, and resistor 3. And the current still flows from positive to negative, but as it crosses this junction, due to Kirchhoff's, it's called Kirchhoff's junction, the current actually has to split, not necessarily in half, it depends on the resistivity on each of the junctions, but the current splits up. So for parallel resistors, the current is no longer constant. So now that the current adds, and the voltage is now constant. And to better understand this, we'll look at an actual example. So let's put in some values. Let's say we have some table here where we know some of the values. So we know that the resistivity of 1 is 1 ohm. We know the resistivity of 3 is 3 ohms. We know the total current going into the circuit to be 27.5 amps. And we know the voltage across resistor 2 is 15 volts. We can use our understanding of Ohm's law, which is still the same and still applicable, to then calculate missing values here. We can also use the fact that that voltage stays the same and current adds. So current total is equal to I1 plus I2 plus I3. And we can use the equation for total resistance. In this case, it's not just the sum of all the resistors. It's actually the sum, or the inverse sum of the inverse of resistors. So to explain what I mean by that, the equation looks like this, where you have 1 over R1 plus 1 over R2 plus 1 over R3, and all of that is inversed. Another way you might have seen it written is 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. So then using this, we can fill in the missing pieces to our table here. If I know that the voltage is constant across this entire circuit, then that means it's 15 volts everywhere. Then I can use essentially Ohm's law to really fill in any of our missing pieces. So here, what we're going to do here is then essentially fill in that using Ohm's law, I get that the current at 3, so I3 is equal to V3 over R3. In this case, it's 15 volts over 3 ohms, so I get 5 amps. I can do the same thing at current 2, equals the voltage at 2 over the resistor at 2, which is 15 volts over 1 ohm, so I get 15 amps. I could then, so I'm going to do it this way, I can then essentially calculate the total resistance. So again, from Ohm's law, resistance then is equal to voltage over the current. So our total is then equal to my 15 volts over my current of 27.5 amps, which if I round to the second decimal place, I get 0.55 ohms. And then I can use either of them to really calculate the missing resistivity, and then Ohm's law to calculate the alternative. It's a little easier to compute current of 2 versus R of 2, but it is possible. We can say that if the total current is the sum of all the currents, then current of 2 is equal to the total minus the current of 1 minus the current of 3, which in this case it is then 27.5 amps minus 15 amps minus 5 amps. And I get that it is 7.5 amps. And then again, I can just use resistivity of 2 is then equal to voltage of 2 over the current of 2. I get running a little bit out of room here, but 15 volts over 7.5 amps. Amps, and I get that it is 2 ohms. You might have noticed that our resistors on each of the individual resistors, the resistance is the exact same as the in-series example we looked at before. So we're going to also look at, the last circuit we're going to look at for resistors, the resistor circuits, are what if we have a combination of resistors that are in series and in parallel to each other, like this example here. And we're going to look at it with exact values as well. So we'll put the table here to show our values that we're going to fill in. We're going to call this V total. This is R1, this is R2, R3, and R4. And we're going to set up some things that we know about this. So the first thing we know is Ohm's law. That has not changed. The current is still equal to the voltage over the resistance. Our total resistance equation has changed now. So if you remember, in series is the sum of the resistors, in parallel is the inverse sum of the inverse. And so the total resistance is going to look something like R1, because that's in series, plus this whole combination of resistors, right? Because that's in series with R1. So it's going to look like 1 over R2 plus R3 and R4 are in series together. They're parallel to R2. So it's 1 over R3 plus R4. And all of that is inversed. So that's our total resistor equation. Our total current equation, I'm going to remember current is constant in series. It adds in parallel. So since R1 is in series, the total current is equal to I1. And then that is then equal to I2 plus I3, where I3 equals I4. Because I3 and I4, since they're in series, it's the same for either of them. They add to the in parallel that is with R2. And then for our voltage equation, V total, remember it's the opposite of the current. It adds in series and it is constant in parallel. So V total is then equal to V1 plus, if it's constant in parallel, then the voltage at 2 has to be equal to the sum of the voltages of 3 and 4. So it's V1 plus V2. Because all of that, once I hit the parallel junction, it stays constant. But then the voltage of 2 is equal to V3 plus V4. And using these equations, at this point it's just algebra. I have some knowns. I have a series of equations with some unknowns, and I'm just going to use this to solve them. The first one being, I'm going to use this to solve the voltage across 4. So this is then saying I have 4 ohms. We add all our units here. Amps, and our voltage. So the voltage is equal to the current times the resistance. So the voltage at 4 is equal to the current at 4 times the resistance at 4, which is 1.3 amps times 4 ohms, and that gives me 5.2 volts. But if I remember, voltage of 2 is equal to the voltage of 3 plus the voltage of 4, because those are in series to each other. So the voltage of 2, and they're parallel to the voltage of 2. So the voltage of 2 is then equal to my 3.91 volts plus my 5.2 volts. 9.11 volts, roughly. And there's going to be a little discrepancy, but that's just from rounding error when we get the voltage total. We look at adding all this up together. So then I can use the fact that I have like essentially two knowns for the resistor 2 to calculate the current at 2, and that's going to equal, so the current at 2, I2 equals V2 over R2, which is going to give me 9.11 volts divided by R2, which is just 2 ohms. I get 4.55 amps. If I round, 4.56 amps. I didn't round that properly, sorry. 4.56 amps. Again, just minor discrepancies from rounding. I know, though, that the current of 2, so also 2, before we continue further, I know the current of 1 is equal to the total current, so this is 5.87 amps. I know the current of 2 plus the current of 3 equals the current of 1, or the total current. So I can use that to solve for the current of 2. No, I've done, sorry, yeah, put that in the wrong spot. 4.56 amps. I also know that the current at R3 and R4 is the same. So the current of 3 is also 1.3 amps. I can then use this to find the resistivity at 3. So R3 equals V3 over I3. And I get that it's 3.91 volts over 1.3 amps. Which, if I round, I get to be 3 ohms. And to calculate, the next value we're going to calculate here is actually going to be the resistance at 1, and we're going to use the total resistance equation for this. So I'm just going to rearrange it. So instead of saying R total, I'm going to say R1 equals R total minus this whole second term here. So R1 is equal to R total minus 1 over R2 plus 1 over R3 plus R4, and all of that inversed. So we get R1 equals the 2.56 ohms minus 1 over 2 ohms plus 1 over 3 ohms plus 4 ohms. All of that inverse. When I plug that into my calculator, I get that R1 is roughly 1 ohm. And then if R is 1 ohm, I know that the voltage equals IR. So the voltage of 1 is equal to the current at 1 times the resistance at 1, which is just 5.87 volts times 1 ohm. Not volts, sorry, amps. Amps times 1 ohm. And I get that it's just 5.87 volts. I can write the unit properly. And then I can use the same kind of setup to figure out the voltage for the total voltage. I get that the total voltage is equal to the total current times the total resistance. And in that case, it is 5.87 times 2.56. And I get that it is roughly 15 volts.